From the moment our ancient ancestors first, gazed up at that glittering tapestry of the night sky, humanity has just been captivated. What is out there really beyond the reach of our hands and even our most ambitious dreams? Where do we fit in?
Right.
Us, this small species on just one world, where do we fit in this grand cosmic ballet?
It's the fundamental question, isn't it?
It really is. It's this age-old curiosity, universal human thing to look up and just wonder. And that sense of wonder, that yearning for understanding, has quite literally shaped our civilization.
And that profound human wonder, that kind of innate curiosity about our place, well, it's driven us, hasn't it? Often through centuries of really painstaking observation, brilliant deductions, and sometimes, let's be honest, profound errors, too.
Oh, definitely.
But it's moved us from simple awe to this complex scientific understanding that, in many ways, is far more profound, I think, and maybe even more beautiful than any ancient myth. This deep dive, it's really going to reveal just how that extraordinary journey from just wondering to a deep scientific understanding has unfolded. It touches on the very nature of existence itself.
All right, let's dive deep then into this incredible collection of sources. They're all centered around the monumental work and vision of, well, one of the most influential voices in science communication ever, Carl Sagan.
A giant. Truly.
His book Cosmos and the discussions surrounding it, that's our foundational material today. Our mission is pretty clear. We're here to extract the most potent ideas, the most surprising facts that don't just illuminate the universe around us, but maybe more importantly, illuminate our own existence within it. We're talking about our true place in the vast cosmos, the incredible unfolding story of life itself, the sheer power of the scientific method, and what all of this astonishing knowledge actually means for our shared future.
And what's truly fascinating here, I think, is how these texts manage to distill such a vast expanse of scientific knowledge. I mean, from the subatomic level all the way up to the supergalactic into a narrative. Yeah. A story that speaks directly to our shared human experience. It's not just about rattling off facts, is it? It's about offering these profound, often quite humbling perspectives on our past, our present circumstances, and our immense potential future.
It really feels like an invitation, doesn't it? To see ourselves not as separate from the universe, but as an integral, evolving part of it all.
Exactly, part of the cosmic fabric.
So let's begin our journey right at the beginning of humanity's sort of organized attempt to understand the heavens, with that universal human tendency to just look up and wonder.
That primal urge.
Imagine ancient civilizations, long before telescopes, before sophisticated math even. Our sources tell us the stars moved across the sky each night with this predictable regularity, right?
Yeah, clockwork almost.
And that prompted people everywhere to ponder their place in it all. This wasn't just idle daydreaming, was it? Or poetic fancy. It was the actual birth of humanity's intellectual journey. Yeah. The very first stirrings of systematic observation, of scientific inquiry.
Indeed. And you had civilizations like the Babylonians, the Egyptians, driven by really practical needs like agriculture, navigation.
Right, knowing when to plant, where to sail.
Precisely. They painstakingly observed these celestial motions. They developed these incredibly sophisticated systems for understanding the heavens, making calendars, tracking planets, even predicting eclipses, which is amazing for the time.
Absolutely.
And that laid a crucial groundwork. These early observational systems, even though they were rooted in cosmological beliefs different from ours, they formed the very foundation upon which later Greek astronomy would build.
So they were starting to bring order to it all.
Exactly. They represent humanity's earliest attempts to bring order to the apparent chaos, the mystery of the night sky, moving from just wondering to actively seeking patterns, meaning predictability. And that foundational curiosity, that drive to understand our surroundings, it's timeless, isn't it? It still propels science forward today.
But this pursuit of knowledge wasn't just about individuals looking up. Here's where it gets really interesting. Imagine a place, a single magnificent institution, where pretty much all the world's knowledge was systematically gathered, preserved, and actively expanded upon. How powerful would that be?
Almost unimaginable power, really.
And our sources vividly describe the Library of Alexandria as precisely that, a truly revolutionary institution. The first place where humans seriously and systematically collected global knowledge on an unprecedented scale. It was just this beacon of intellectual ambition.
The approach they took to acquiring knowledge at Alexandria was, well, it was simply revolutionary for its time. They literally sent agents out with vast sums of money to buy up entire libraries.
Wow.
And famously, the harbor police in Alexandria would search commercial ships not for contraband, but for books.
No way. Seriously.
Seriously. Any scrolls found were confiscated, copied by the library scribes, and then the copies were returned to the owners while the originals were kept for the library.
That's audacious.
It was. And this approach fostered an environment of just unparalleled genius. It brought together brilliant minds from all across the known world, figures whose contributions, well, they still resonate today.
Like who? Give us some names.
Okay, well, you have Eratosthenes, who brilliantly calculated Earth's circumference with remarkable accuracy, using just simple geometry and observation.
That's the one with the shadows, right? In Cyan and Alexandria.
That's the one, just sticks and shadows. Then there's Hipparchus, meticulously mapping constellations, categorizing star brightness. Euclid, his elements, is still the bedrock of geometry.
Of course.
Dionysius of Thrace gave us parts of speech. Herophilus, who daringly established the brain, not the heart, as the true seat of intelligence.
Challenging ancient beliefs.
Big time. Heron of Alexandria inventing early steam engines, automata. Apollonius of Perga detailing conic sections, paving the way for Kepler's later understanding of orbits. And of course, Archimedes, a mechanical genius centuries ahead of his time.
What a lineup.
It really was. And this grand endeavor, the library itself, it was so much more than just a building with scrolls. It was a living symbol of humanity's organized, collective pursuit of knowledge. And its destruction.
Yeah.
Along with the loss of maybe 500,000 handwritten papyrus scrolls, it was a profound, irreplaceable tragedy. It echoes through history, reminding us how fragile our accumulated wisdom really is.
The loss of the library. It's just staggering to think about. A real wound in our collective memory. It makes you wonder, how much we might have missed or how much progress was delayed. Like Aristarchus of Samos. He was one of the last Ionian scientists whose works were there. He had this book arguing a truly revolutionary idea that the Earth orbits the sun.
The heliocentric model, yeah. Centuries before Copernicus.
Exactly. And that stars are immensely far away, not just little lights stuck on a dome, both totally correct. But because his work was lost, or mostly ignored,
He had to wait.
we had to wait nearly 2,000 years for Copernicus and others to rediscover it. Our sources lament, and I'm quoting here, "If we multiply by 100,000 our sense of loss for this work of Aristarchus, we begin to appreciate the grandeur of the achievement of classical civilization and the tragedy of its destruction."
That puts it starkly.
It really does. Imagine the shift in mindset if heliocentrism had been accepted back then. How might the scientific revolution have unfolded differently? Or just sooner? The destruction wasn't just lost scrolls, it feels like a lost trajectory for human understanding. We had to retread ground for millennia.
That's a really powerful point, and it challenges us, doesn't it? Because the initial resistance to Aristarchus's idea, it wasn't based on evidence, was it? It was often dismissed as impiety or just philosophical dogma.
Right, like the Platonists thinking Earth was too tainted, too imperfect for the center.
Exactly, which stands in stark contrast to that earlier Ionian awakening, where free inquiry, observation, logical deduction, those were highly valued. It's a really stark lesson in how powerful ingrained beliefs can be in, well, stifling intellectual progress.
And this resistance, this preference for dogma over just looking at the evidence, it continued for a very, very long time. The geocentric model, especially Ptolemy's detailed system with Earth fixed at the center.
It dominated Western thought for centuries.
Absolutely. And the prevailing assumption, even for brilliant minds like Pythagoras, Plato, Galileo, Tycho, even Copernicus himself for a long time, was that planets had to move in perfect circular paths.
That aesthetic ideal of perfection.
Right. Copernicus, even when he proposed his sun-centered model, he initially struggled to break free from circular orbits because, as he said, the mind shudders at non-circular motion. He thought it would be unworthy in a creation constituted in the best possible way.
It's fascinating, isn't it? How deeply ingrained beliefs about cosmic perfection or humanity's central importance, even without any real empirical basis, can shape our understanding and just impede progress for so long.
It took immense courage to challenge that.
Immense intellectual courage, yeah, and often great personal risk. And even today, centuries later, our everyday language still reflects that geocentric past, doesn't it?
We still say sunrise and sunset.
Exactly. We
Yeah.
talk about the sun rising, the sun setting, even though we know full well it's the earth turning. It just highlights how profoundly our perceived place can influence our language or unconscious understanding. It's a powerful reminder of how hard it is to shake off old ways of thinking.
So what does this all mean for understanding our actual place? As we slowly moved from Earth-centered to sun-centered views, we also started developing better ways to measure the sheer, almost incomprehensible scale of the cosmos, getting our first real glimpses of the infinite. Like Christian Huygens. Working in that spirit of free inquiry, he brilliantly estimated star distances just by comparing the sun's apparent brightness to Sirius.
Even with the imprecise data he had back then.
Right. But the clarity, the elegance of his method, it laid crucial groundwork for more accurate measurements later. He showed us how to even begin mapping the truly vast distances out there.
Indeed. And to really grasp those scales, we had to introduce the concept of a light year, a unit of truly enormous distance.
It's hard to wrap your head around.
It is. It's nearly 10 trillion kilometers, or about 6 trillion miles. That's how far light, the fastest thing there is, travels in just one Earth year.
And light is incredibly fast, 186,000 miles in a single second.
Exactly. It takes sunlight just 8 minutes to reach us. But the nearest star, over 4 light years away.
4 years at the speed of light.
Wow. And when we look out further, we see galaxies. Carl Sagan described them so evocatively as sea froth on the waves of space, each one composed of not just a few stars, but billions upon billions of stars.
Our own Milky Way has hundreds of billions.
Hundreds of billions? And the sheer numbers, they're just mind-boggling, almost beyond our capacity to really comprehend.
Our sources say there are maybe as many planets as stars in all the galaxies in the observable universe. What was the number? 10 to the 22.
10 billion trillion planets. Just try to picture that. It's an ocean of worlds out there.
It really is.
And this immediately raises that profoundly important question, doesn't it? The one that strikes right at the heart of our perceived uniqueness.
Which is?
Well, in the face of such overwhelmingly vast numbers, billions of galaxies, each with billions of stars, and likely billions, maybe trillions, of planets, what is the likelihood that only one ordinary star, our sun, is accompanied by an inhabited planet?
Seems pretty slim when you put it like that.
Why should we, tucked away in some forgotten, unassuming corner of the cosmos, be so exceptionally fortunate, so singularly special? To me, and frankly to many scientists, it seems far, far more likely that the universe is just teeming, brimming over with life.
It really encourages you to question that assumption of uniqueness.
Absolutely. And to consider the overwhelming probability of life existing beyond Earth, we're really just beginning our explorations, aren't we? Just on the cusp of understanding life's true place in this grand cosmic tapestry.
All right, now let's zoom in a bit. Moving from that grand cosmic scale of planets and galaxies down to the intricate, almost microscopic workings that underpin life itself right here on Earth.
Yeah.
And our sources kick this off with something genuinely bizarre but totally illuminating. The Heike crabs.
Ah, yes, the samurai crab.
I mean, a crab that looks uncannily like a samurai warrior. That's just wild. But what does it actually tell us about the profound scientific principle of selection in nature?
Well, the story of the Heike crabs, found in the Japanese inland sea, it's a perfect example of what Darwin called artificial selection. Their shells, carapaces, have these patterns that look disturbingly like the scowling face of a samurai.
It's really uncanny.
It is, and it isn't a coincidence. After the Battle of Dano-Ura back in 1185, where the Heike samurai clan was defeated and many drowned, the local fishermen developed this custom. In commemoration, they'd throw these crabs, especially those with even a slight resemblance to a human face, back into the sea. They believed they were reincarnated spirits of the fallen warriors.
So they were selecting for the samurai face.
Exactly. This preferential sparing meant crabs with even a subtle samurai-like look were allowed to reproduce more, while the others were kept and eaten. Over generations, this selection imposed from the outside, by human preference, not natural pressures, led to these crabs with increasingly fierce, scowling samurai faces.
That's the core of artificial selection, then.
Precisely. Humans, for whatever reason, aesthetic, superstition, utility, encourage some varieties to reproduce and discourage others, leading to sometimes dramatic changes in species over time. Think dog breeds, agriculture.
Right. And the beauty of this example is how it leads us straight to Darwin's much broader idea of natural selection.
If humans can do it artificially.
Why couldn't nature itself, through its own mechanisms, do the same thing on an infinitely larger scale? Darwin argued that inherited traits are fundamental, right? And that nature acts like a selective force, just like a human breeder.
But with different criteria.
Exactly. Nature's criteria aren't human preferences, they're survival and reproduction in a given environment. More individuals are born than can possibly survive, so.
So those with even the slightest advantage, as Darwin put it, maybe better camouflage, a more efficient way to find food, resistance to disease, they're more likely to survive and pass on their genes.
Leading to gradual changes over vast stretches of time.
It's this relentless, elegant process of trial and error in nature, constantly refining species to fit their environment. Our sources even shared that funny anecdote about the fruit fly, the Drosophila moth.
Oh yeah, the one mistaken for a macromutation.
Right. It was just another lovely adaptation in nature itself, the product of tiny mutations and natural selection, just trying to get at the lab's molasses. Nature is always, always at work.
And this whole intricate, beautiful process of evolution, it's fundamentally driven by the blueprint of life itself. DNA.
The master molecule.
It's described as the master molecule of life on Earth, a truly astonishing piece of molecular machinery. Structurally, it's that twisted ladder, the double helix.
Yep, with rungs made of those 4 molecular parts, the nucleotides. A, T, C, and G.
And the specific sequence of those nucleotides forms the genetic code. Literally the instructions for building and operating an organism. A mutation, then, the raw material for evolution.
Is simply a change in one of those nucleotides, a tiny alteration in the code, a typo, basically, which then gets copied and passed on.
And most mutations are harmful, right?
Understandably, yeah. Most are harmful or even lethal, often making non-functional proteins. But it's that rare, improbable, beneficial mutation, that lucky typo,
that drives evolution forward.
Exactly. It provides the novelty, the variation upon which natural selection can actually act.
It's truly incredible to think about the scale of this molecule. A single human DNA molecule has, what, 100 million twists? And 100 billion atoms?
As many atoms as stars in a typical galaxy. It's mind-blowing.
And the sources highlight the incredible precision of the machinery involved, like a DNA unwinding enzyme, helicase.
The molecular zipper.
Yeah, unzipping the helix so it can be copied. And then DNA polymerase, which meticulously proofreads the DNA as it copies, catching and fixing almost all the errors.
Almost all, but not quite all.
Right. It's those rare, uncorrected errors, those persistent typos that cause the mutations, fundamentally changing the instructions and providing that essential variability for life's long, slow adaptation.
And what's truly fascinating here, I think, is how this incredibly intricate molecular machinery operating down at the submicroscopic level underpins the spectacular diversity of life we see all around us.
From bacteria to blue whales.
Exactly. And yet, this very complexity points to a profound underlying unity. The molecular unity of life on Earth, the fact that the same genetic code, the same basic biochemical processes are used by trees, people, fish, slime molds.
Everything.
Pretty much everything. It strongly suggests a single common origin of life on our planet. It sort of dissolves the apparent barriers between species, doesn't it? It transforms biological diversity into this profound testament to a shared cosmic heritage.
It suggests the recipe for life might be universally accessible, not some one-off miracle.
Precisely. Which leads us right to the ultimate question of life's origins and, maybe even more excitingly, the search for it elsewhere in the universe.
And what a question that is. One that's captivated humanity for centuries. Experiments like those at Cornell University have simulated the conditions thought to exist on primitive Earth.
The Miller-Urey type experiments, yeah.
They mixed gases like hydrogen, water, ammonia, methane, even hydrogen sulfide stuff we know was around on early Earth and is common in the cosmos today. Then they sparked these mixtures, simulating lightning, a common energy source back then. And the result?
A rich collection of complex organic molecules. Amino acids, nucleotides, the building blocks of life.
Spontaneously created, which suggests that the stuff of life can be very easily made under surprisingly common conditions.
And that has a profound implication, doesn't it? It suggests that given enough time, the origin and evolution of life might not be some rare, unique event, but maybe a cosmic inevitability.
Even if it takes wildly different forms on other planets.
Absolutely. Dictated by their unique environments, it's a huge shift from thinking life is a unique miracle. And this compelling quest, this yearning to know if we're alone, it led us quite naturally, maybe a bit optimistically, to our nearest planetary neighbor, Mars.
Oh, Mars. Here's where it gets really interesting. We went looking for Martians, didn't we? And what we found was both tantalizingly intriguing and ultimately frustratingly ambiguous.
The canals.
Exactly. For decades, especially late 19th, early 20th century, figures like Percival Lowell were absolutely convinced of Martian canals, and therefore, an ancient, wise civilization that built them to manage water on a dying planet.
Fueled by the engineering marvels of the time here on Earth, like the Suez and Panama canals.
Right. Lowell was sure Mars was Earth-like, just older and drier, crisscrossed by these vast irrigation ditches, but not everyone bought it.
No, people like Alfred Russel Wallace were highly critical, arguing the conditions made such life, especially civil engineers interested in hydraulics, pretty much impossible.
A bit dryly put by Wallace there.
A bit, yes. So the Viking landers, they touched down in 1976, a truly ambitious mission, explicitly designed to search for life.
But they had limits on where they could land, right?
Big limits. Not too high, not too windy, not too hard, not too soft, crucially not too rough, which basically confined them to relatively dull, flat plains from a geological perspective.
Not exactly where you might expect life to be thriving.
Perhaps not. Once on the surface, they ran sophisticated experiments, including those Mars jars, sealed chambers simulating the Martian environment. They put terrestrial microbes in.
And what happened?
Well, many died, as expected. But some varieties, ones that didn't need oxygen or could hide from UV light or shut down in the cold, actually survived. And in some cases, with a bit of liquid water added, they even showed signs of growth.
That sounds promising.
It was exciting. It hinted at a robustness of life we hadn't fully appreciated yet. The overall results were contradictory. They left scientists scratching their heads.
Oh, so.
While some of the microbiology experiments suggested metabolic activity, things consistent with life. The crucial organic chemistry experiment found not a hint of organic matter in the Martian soil.
Which led to that famous question.
Where are the dead bodies? Exactly. If life existed, even microbial life, where were its organic remains? The carbon compounds that are its building blocks, it's still one of the great mysteries of Mars.
What are the possible explanations?
Could be a really oxidizing surface chemistry that just destroys organics quickly. Or maybe, just maybe, life on Mars, if it exists, is based on a fundamentally different chemistry than ours. Truly alien.
That ambiguity forces us to consider that life might exist in forms we don't even recognize or know how to look for yet.
Absolutely. And it's fascinating that even the concept of terraforming Mars, that grand dream of reshaping it for humans, implicitly acknowledges our growing power to impact planetary climates.
It draws a parallel to what we're doing to Earth's climate.
A direct and quite sobering parallel. The burning of fossil fuels, deforestation, changing Earth's climate through the greenhouse effect. Venus, with its runaway greenhouse, stands as the stark warning, doesn't it? A possible future if we don't understand and manage our impact. It really emphasizes the delicate balance of planetary systems and our often unwitting influence on them.
Speaking of human intelligence and our capacity to impact planets, our brains, they're not just powerful, they represent this ongoing miraculous evolution of information processing, allowing us to adapt in ways our genes just can't.
Right. Our sources describe the brain's evolution like layers, built from the inside out, like a city growing haphazardly over millennia, older parts still working alongside the new.
What are the layers?
At the core, the oldest part, the brainstem. Basic survival functions, breathing, heart rate, temperature, stuff we don't think about.
The autopilot.
Pretty much. Wrapped around that is the R complex, our reptile brain. Primal instincts, aggression, territoriality, ritualistic behaviors we share with ancient reptiles.
Still in there.
Oh yeah. Then the limbic system, center of emotions, bonding, drives, makes us mammalian. And finally, the crowning achievement. The huge, convoluted cerebral cortex, massively expanded in humans, abstract thought, language, learning, memory, consciousness itself.
And all these layers are still active, interacting?
Constantly, in a complex, subtle interplay, giving us both our primal urges and our soaring intellect. And the information capacity stored in there is just staggering. Our knowledge, our consciousness, it's encoded in neurons, about 100 billion of them.
Yeah.
Roughly as many as stars in the Milky Way. And each neuron can have thousands of connections to others.
Leading to?
Something like 100 trillion connections in the human cortex alone. This incredibly intricate network forms the elegant architecture of consciousness.
And the brain has those dual strengths.
Yeah.
Left and right hemispheres.
Exactly. The right hemisphere often linked with pattern recognition, intuition, creativity. The left more with rational, analytical thought, language. And the dialogue between them through that massive nerve bundle, the corpus callosum, is crucial for generating ideas, testing them, building our understanding.
It's astounding how much information we process. Our genes hold a few billion bits.
Our brains maybe 10 times more.
And all the books in libraries,
Oh, yeah.
10,000 times more than our genes.
Takes our cultural knowledge and perspective, and then you have whales.
Ah, the whales.
Yeah.
Their communication network is incredible.
Astonishing. Using those super low frequency sounds around 20 hertz that travel vast distances across entire oceans, thousands of miles sometimes.
And they remember songs.
Incredible memory for complex songs, yeah. Remembering them for months, years, constantly evolving them. It's like cultural transmission.
So, if creatures like whales can achieve that, what does it tell us about intelligence beyond just us?
It expands our whole concept of intelligence, doesn't it? And adaptability, information processing. The ultimate takeaway from studying the brain, from its ancient roots to its complex present, is that we can change ourselves.
Unlike the fixed programming of the reptile brain.
Or the slow pace of genetic evolution, yeah. Our cortex allows us to learn, adapt, make conscious choices, fundamentally change who we are and how we interact with the world, way faster than biology alone ever could. It's our greatest tool for survival and progress.
Okay, let's unpack this next section. We're turning our gaze back out to the broader cosmos, looking at some of the truly dramatic events that shape it. And starting with comets. Our understanding has completely transformed, hasn't it?
Dramatically. From portents of doom to icy snowballs.
Historically, yeah, they were seen as terrifying omens, prophecies, heralds of doom, and big changes. Like Halley's Comet in the Bayeux Tapestry in 1066.
Widely believed to be predicting William the Conqueror's invasion.
Right, or again in 1301 when Giotto saw it and put it in his famous painting.
But then, over time, science began to demystify them. Brilliant minds like Tycho Brahe, with his meticulous naked-eye observations.
And Isaac Newton, of course.
Newton, with his laws of gravitation, revealed they weren't random apparitions or divine signs at all. They moved in predictable, although very eccentric, elliptical orbits around the sun, just like planets.
He called them a sort of planets revolved in very eccentric orbits.
Exactly. This demystification was crucial. It allowed Edmund Halley to confidently predict the comet's return in 1758, a stunning triumph for Newtonian physics. And understanding them was crucial because, well, they can hit us.
Like the Tunguska event.
Tunguska, 1908. That vast explosion that flattened 2,000 square kilometers of Siberian forest but left no crater. Compelling evidence that a comet fragment, mostly ice and dust, exploded high in the atmosphere.
An airburst.
A massive airburst, equivalent to a 10 or 15 megaton nuclear blast. Eyewitnesses described fire, a deafening roar, a powerful shark wave. And meteors, we now know, are often just remnants of old comets or asteroids, tiny bits of cosmic debris burning up in our atmosphere, those shooting stars.
So what does this all mean? Comets went from omens to identifiable objects, basically giant tumbling snowballs about 1 kilometer across, orbiting the sun, their tails always pointing away because of the solar wind.
And the sources emphasize that while big impacts are rare, even rare events happen over cosmic timescales, hinting at the possibility of future encounters that could, well, dramatically affect our planet.
Which leads us to another major shaping force, impacts from space. The moon's surface, right?
Yeah.
Covered in craters.
Billions of them. It's eloquent testimony of a previous age of the destruction of worlds, as the source puts it. A visual record of when the solar system was a much more violent place.
But Earth looks so different.
And what's truly fascinating here is that stark contrast. The moon, airless, waterless, no geology to speak of it, preserves those impact scars for billions of years. It's like a geological archive of collisions.
Whereas Earth
is dynamic, running water, wind erosion, active volcanoes, plate tectonics, building mountains, reshaping continents. These slow internal processes efficiently wipe out or fill in even huge craters over millions of years. Meteor Crater in Arizona is relatively recent, geologically speaking, and it's rare precisely because our planet is constantly resurfacing itself.
So moon dominated by external catastrophe, Earth by internal slow change.
Pretty much. External catastrophic events dominate the moon's history. Internal, slow, continuous processes dominate Earth's, constantly rejuvenating the surface. Mars, interestingly, is kind of an intermediate case. Clear signs of ancient impacts, but also signs of past geological activity, like old riverbeds, hinting at a more dynamic past than it has today. Each world tells a different story of its history.
Now let's take that grand tour of the solar system, venturing beyond Earth to see the incredible diversity out there. First stop, our cloudy neighbor, Venus.
Ah, Venus. Initially, because of those thick, impenetrable clouds, astronomers just, well, misinterpreted it completely.
Leading to speculation about swamps, jungles, maybe dinosaurs.
Widespread speculation. The logic often seemed to be, as the source notes, observation, there was absolutely nothing to see on Venus. Conclusion, it must be covered with life. It was optimism over evidence, really.
This raises an interesting question, doesn't it? About scientific development itself.
How so?
Well, if science on Earth was spurred by seeing the heavens, how would an intelligent civilization develop science on a planet like Venus, where the sky is just permanently hidden by clouds?
That's a great question. Our sources highlight how our prejudice toward visible light limited our understanding. It took new tools, spectral analysis, looking at the light that did get through and reflect back, to finally unravel Venus's true hellish nature. An atmosphere that's 96% carbon dioxide, clouds of sulfuric acid, creating an absolutely massive greenhouse effect, surface temperatures hot enough to melt lead.
Wow. How does that work exactly?
Sunlight gets through the CO2 atmosphere easily enough, heats the surface, but then the infrared radiation, the heat trying to escape back into space, gets trapped by the CO2 and water vapor. It just builds up and up, a runaway effect.
Turning Venus into a planetary inferno, like a plastic helmet would just melt there.
Instantly. It's a powerful natural laboratory, showing us what happens when a greenhouse effect spirals completely out of control. A potential warning for Earth, perhaps.
Okay, next stop. Jupiter and its amazing moons. Jupiter itself is just colossal.
A true giant. Mostly hydrogen and helium, no solid surface to speak of. You could fit 1,000 Earths inside it.
1,000. But it's the moons, the Galilean moons, that are maybe even more fascinating, like a mini solar system.
They really are. Each one a unique world with its own dramatic story. Let's start with Io, the innermost large one.
The volcanic one.
Intensely volcanic, its surface is constantly changing, hundreds of active volcanoes spewing molten sulfur and sulfur dioxide. It literally looks like a pizza pie with all those colors: red, orange, yellow.
What causes all that activity?
Immense tidal forces. From Jupiter, mainly, but also the other Galilean moons, they constantly need Io's interior, keeping it molten.
Okay, then Europa.
Europa. Remarkably smooth, like a billiard ball, but crisscrossed with these intricate dark lines. They're thought to be cracks in a thick ice shell.
Hinting at.
A vast, salty, liquid water ocean beneath, heated by similar tidal forces. This makes Europa one of the absolute prime candidates for finding life elsewhere in our solar system.
An ocean under the ice. Amazing. What about Ganymede and Callisto?
Further out, Ganymede is the largest moon in the entire solar system, bigger than Mercury. It is grooved terrain alongside older cratered regions, suggesting a really complex geological history. And finally, Callisto, the outermost, has this ancient, heavily cratered surface, indicating very little geological activity since it formed way back. Jupiter's moons are just a testament to the diverse ways worlds can form and evolve.
And finally, let's look at Saturn, with those mesmerizing rings, and its most intriguing moon, Titan.
Saturn, similar to Jupiter in composition, a gas giant. Famed, of course, for its spectacular, intricate ring system, countless icy particles, from dust grains to boulders. But among its many moons, Titan really stands out.
Why Titan?
It's unique in our solar system, the only moon with a substantial, dense atmosphere, even thicker than Earth's.
Thicker than ours, wow. What's it made of?
Mostly nitrogen, like Earth's, but also rich in methane. And UV light from the sun constantly breaks down this methane into more complex hydrocarbons,
which then
fall to the surface, potentially covering Titan's landscape in a brownish, tarry organic sludge. A vast repository of organic molecules.
So the building blocks of life are abundant there.
Incredibly abundant. Even though it's extremely cold, it's an environment where the raw materials for life as we know it are just everywhere. It really pushes us to consider how life might adapt and emerge under truly alien conditions, maybe using different solvents, different energy sources.
It goes back to Huygens, who discovered Titan, right? He wondered if the wise creator would leave such worlds bare and destitute of inhabitants.
That profound human curiosity, yeah. It persists to this day. How could such potential go unrealized?
So what does all this mean for our exploration? These incredible discoveries, these stunning portraits of other worlds, they were made possible by missions like Voyager.
Audacious missions. Launched back in 1977, the twin Voyagers took advantage of that rare planetary alignment. Happens only once every 175 years or so.
Allowing them to slingshot from one giant planet to the next.
Jupiter, Saturn, Uranus, Neptune. Before continuing their journey out of our solar system, becoming humanity's first true interstellar travelers. Still going, too.
They were monumental, weren't they? They completely reshaped our understanding of the outer solar system, returned over 100,000 photographs.
Gave us that unprecedented family portrait of the solar system, and maybe most famously, one of the Voyagers captured that iconic pale blue dot image of Earth.
Just a tiny speck of light.
Suspended in a sunbeam. It embodies Sagan's profound visual approach to understanding our place. And these spacecraft, they also carry that symbolic message, don't they?
The golden record.
Yeah, for any interstellar civilizations they might encounter. A gold-plated copper record with sounds, images portraying life and culture on Earth, scientific info on how to play it, Earth's position, our epoch. A message in a bottle cast into the cosmic ocean.
It's truly humbling. Voyager isn't just a machine, it feels like our emissary, carrying humanity's story, our curiosity, our dreams out to the stars, maybe for billions of years.
It's a modern traveler's tale, isn't it? Its discoveries are like the fantastic, sometimes true, stories brought back by early explorers like Marco Polo or Zhang He, expanding our understanding not just of the universe, but profoundly of ourselves and our unique place within it, a testament to our ingenuity and our enduring drive to explore the unknown.
Okay, let's unpack this next segment. It gets pretty mind-bending, dealing with the very fabric of reality itself. Starting with the lives of the stars, those colossal cosmic furnaces lighting up the universe.
Right. Stars are born, essentially, from gravity. Huge, cold clouds of gas and dust out in interstellar space start to collapse under their own weight.
Gravity pulls them together.
Exactly. As the cloud contracts, the material in the core gets incredibly dense, heats up tremendously, and this keeps going until the temperature and pressure at the very center becomes so extreme.
That nuclear fusion ignites.
Precisely. Hydrogen nuclei start fusing into helium. 4 hydrogens make 1 helium, releasing an immense amount of energy, mostly high-energy gamma rays initially.
And that energy pushes outwards.
It creates an outward pressure that perfectly balances the inward pull of gravity. That creates a stable state. Our sun, for instance, has been in this stable phase, its main sequence, for about 5 billion years now.
Converting how much hydrogen?
A staggering 400 million tons of hydrogen into helium every second. It's basically a perfectly contained, continuous hydrogen bomb powering our whole solar system, making life here possible.
So everything we see in the night sky.
Pretty much everything shining up there is doing so because of distant nuclear fusion, the same process fueling our sun. But stars don't live forever. They have dramatic lives, often violent deaths.
Depending on their mass, right?
Exactly. They can explode as spectacular supernovae, briefly outshining entire galaxies. And what's left behind can be incredibly dense remnants. White dwarfs, held up by the quantum pressure of electrons.
Or even denser neutron stars.
Where protons and electrons are crushed into neutrons. And the most massive stars of all collapse completely into black holes regions where gravity is so intense that nothing, not even light, can escape.
This journey from vast stars down to their building blocks brings us to the fundamental nature of matter itself. Atoms and beyond. Like, everyday objects seem solid, right? This table, my hand.
They seem solid, yeah, but at the atomic level, they're mostly empty space. Which leads to that great question from Arthur Eddington.
Why do the nuclei that comprise my elbow not slide effortlessly through the nuclei that comprise the table?
Exactly. And the answer lies in electrical forces. Objects hold together not because they're physically solid, like we imagine, but because the electron clouds of their atoms repel each other powerfully. Those electrical forces prevent them from sliding through each other or collapsing.
And what's fascinating is the simplicity at the heart of it all.
Incredible simplicity, hiding immense complexity. Atoms are basically made of just 3 fundamental particles. Protons, positive charge, electrons, negative charge, and neutrons, no charge.
And different combinations make different elements.
Right. Different numbers of protons and neutrons in the nucleus, surrounded by electrons, form the 92 naturally occurring chemical elements that make up everything we see and touch. You know, the alchemist's dream of changing elements.
Turning lead into gold.
Theoretically, at a subatomic level, it's sort of possible. Subtract a proton and 3 neutrons from mercury, you get gold. But the quest for what's even more fundamental continues. Physicists now think protons and neutrons themselves are made of smaller particles called quarks.
Which raises that philosophical question.
Infinite regression. Are quarks the ultimate building blocks? Or are there layers within layers, endlessly? It's a puzzle still driving particle physics today.
And when we talk about vastness, it's not just space or stars. The numbers describing the universe's particles are immense, challenging our comprehension.
Like the Google?
Right, a 1 followed by 100 zeros. And then there's the Googleplex, which isn't just bigger, it's astronomically larger, 10 to the power of a Google.
It's hard to even conceive. To give some context, the total estimated number of elementary particles, protons, neutrons, electrons in the entire observable universe is about 1080.
Which is huge, but
Still vastly, vastly less than a Google. A Googleplex is so unimaginably immense, if you try to write it out, there isn't enough space in the entire observable universe to hold all the zeros.
these numbers aren't just big, they humble our ability to comprehend scale. Infinity is something else entirely.
Absolutely. It highlights that these numbers, immense as they are, don't even begin to approach infinity. A Googleplex is precisely as far from infinity as the number 1 is. It's a concept that just stretches our minds to the limit. And this ongoing quest to understand the truly fundamental units, the scales the universe operates on, it's one of science's great unfinished symphonies.
Now, let's talk about gravity's most extreme effects, where the universe really starts sounding like science fiction, but it's based on solid physics,
Yeah.
black holes and warp space.
Right. A black hole, simply put, is a region where gravity is so incredibly intense that nothing, not even light, the fastest thing there is, can escape once it crosses a certain boundary, the event horizon.
They form from collapsing massive stars.
At the end of their lives, yeah. But how do we even begin to think about something we can't directly see? Einstein's general relativity revolutionized things. Gravity isn't just a force.
It's a distortion in the fabric of space-time itself.
Exactly. Our sources use the flatland analogy to help visualize it. Imagine our 3D space being locally warped or puckered into a fourth physical dimension we can't perceive, like a bowling ball on a stretched rubber sheet.
So a black hole is like
A literal bottomless pit in that sheet. Or, as Sagan put it, a cosmic Cheshire cat, invisible from the outside, but its gravitational presence is unmistakable, influencing everything around it.
And the theoretical possibilities get even wilder. Wormholes.
Yeah, hypothetical tunnels through space-time, acting as interstellar or intergalactic subways, maybe even time machines. The fact that these ideas are discussed even semi-seriously shows just how surreal the universe might be.
And quasars might be related.
It's theorized that quasars, those incredibly energetic objects in the distant universe, might actually be immense, supermassive black holes at the centers of young galaxies, fueling their incredible energy output as they gobble up surrounding matter.
This is truly where science sounds like the wildest sci-fi, but it's grounded in profound insights about how the universe actually works. And these insights extend to the grand architecture of galaxies and the expanding universe.
Galaxies themselves are vast cosmic islands, collections of billions, sometimes trillions of stars, plus enormous clouds of gas and dust. Our Milky Way alone has maybe 400 billion stars.
And they come in different shapes.
Different types, yeah. Majestic spirals like ours, smooth ellipticals, chaotic irregulars. And they can collide, distorting each other in these slow-motion cosmic dances over millions of years.
But when galaxies collide, the stars don't actually crash into each other much.
Rarely. Because a galaxy is mostly empty space. The stars usually pass right by each other, like bullets through a swarm of bees, as the source says. But the immense gravitational forces and the friction between the gas and dust clouds do severely distort the overall shapes, sometimes creating rare ring galaxies or merging into larger ellipticals.
And the whole universe itself is expanding.
Not static at all, it's expanding. The evidence is the redshift of distant galaxies. It's a Doppler effect. Their light gets stretched to longer, redder wavelengths as they move away from us, like the pitch of a siren dropping as it passes.
And there's the cosmic background radiation, too.
Exactly. That faint, uniform static of radio waves from all directions. It's the lingering afterglow of the Big Bang itself, like finding the faint warmth of a cooling oven, confirming the universe was once much hotter, denser, and has been expanding and cooling ever since.
And this expansion means things are moving incredibly fast out there. Some quasars are receding at over 90% the speed of light.
Mind-boggling speeds. Milton Humason, that fascinating figure who started as a mule skinner on Mount Wilson and became a pioneering astronomer.
He measured many of these galactic spectra, right?
He was instrumental, meticulously documenting the red shifts that helped establish the expanding universe model. But the interpretation isn't totally without debate.
Oh.
Well, Halton famously challenged the standard view, pointing to cases where galaxies with small redshifts seem physically connected to quasars with huge redshifts. If true, it suggests redshift isn't always just about distance or velocity. It implies something very strange is going on in the depths of space that our current models don't fully explain.
Science has never truly settled them.
It underscores that constant refinement based on observation. And our sources even touch on that really speculative idea of the universe maybe having gone through many oscillations, cycles of expansion and contraction, with the laws of nature potentially reshuffled each time.
Making our existence seem like an extraordinary coincidence.
A cosmic slot machine, yeah. That this time around the universe came up with physical laws perfectly consistent with us. The universe itself is telling this ancient, colossal story, galactic dances, fundamental expansions, maybe contractions, and we're really only just beginning to decipher its deepest secrets.
Here's where it gets really interesting, maybe even personal. As we ponder the vastness of the cosmos, the immense sweep of time, the true measure of our intelligence, our resilience, it might not just be in our individual brains, powerful as they are.
Where else then?
In our collective ability to store and share knowledge across millennia. The human record, written words, libraries, plays this vital, almost sacred role in accumulating and transmitting knowledge across generations.
Libraries really do let us voyage through time, don't they? You can sit with Socrates, learn from Da Vinci's observations, follow Einstein's equations.
Tapping into the collective consciousness of our ancestors.
And accelerating human progress far beyond the limits of just oral tradition, which is so vulnerable to loss, to distortion. The sheer volume of information is staggering. An hour of TV might be 112 bits, our brains maybe 1013.
But all the books in Earth's libraries.
Something like 1016 to 1017 bits, 10,000 times more than our genes, over 1,000 times more than our individual brains. Our sources argue that how we support libraries, institutions like them, directly reflects the health of our civilization.
Our awareness about the underpinnings of our culture.
And our genuine concern for the future. It's our collective memory, bridging millennia, allowing continuous innovation.
But now let's turn to the fragility of existence, drawing urgent lessons from the past, profound warnings for the future. Like the dinosaurs' extinction 65 million years ago.
A catastrophic event wiped out the dinosaurs, many other species, clearing the way for mammals, including our own ancestors eventually, a dramatic turning point.
What caused it? There were a couple of ideas, right?
For decades, yeah. Two main hypotheses. One was a nearby supernova explosion, intense cosmic rays spraying Earth, depleting the ozone layer, exposing life to deadly UV radiation.
Frying everything.
Pretty much. The other, now widely accepted, is a large asteroid impact, throwing up immense dust clouds, blocking sunlight for months, years, causing rapid global cooling, plant death, food chain collapse.
And the sources say.
Soberly note that over hundreds of millions of years, both events must have happened at least once, highlighting that Earth isn't immune to these cosmic dangers. It underscores the inherent fragility of life on any planet, ours included, when faced with such events.
Which brings us to a terrifying, self-inflicted potential catastrophe: nuclear war. For the first time ever, humanity has the power not just to affect regional climate, but potentially alter the global climate and, terrifyingly, self-destruct with nuclear weapons.
It's a dreary chain of causality that's led to this perilous state of nuclear proliferation. Many nations with arsenals capable of ending civilization as we know it.
The consequences are almost unimaginable.
Beyond the immediate blast, the firestorms incinerating cities, there's the widespread, deadly radioactive fallout. Think of Rangala-Bakal.
From the nuclear tests.
Yeah, inhabitants got an average dose of 175 rads, widespread thyroid problems, cancers, but the long-term effects are even scarier. Massive ozone depletion causing skin cancer, immune suppression, profound ecological disruption, maybe a nuclear winter devastating agriculture, widespread plagues, mutations, total loss of medical care, deep, enduring psychological trauma for survivors.
It's horrifying. L.F. Richardson's statistical analysis of wars
showed war is murder writ large. And his chilling extrapolation suggests nuclear weapons move humanity much closer to doomsday, potentially killing everyone. Which raises that incredibly important question for us as a species.
If we understand the mechanisms of conflict, why do we keep preparing for war?
Exactly. If we can statistically analyze how violence escalates, why do we continue to prioritize preparations for war, building ever more destructive weapons, overinvesting in understanding and preventing the conflicts that could undo us? Why spend so much on arms and so little on disarmament?
So what does this all mean for our chances of long-term survival? We have this incredible intelligence, this capacity for learning, but also, as the sources say, dangerous evolutionary baggage.
Hereditary propensities for aggression and ritual, submission to leaders, and hostility to outsiders. Deeply ingrained stuff from our past.
Our survival really depends on which part wins out, doesn't it? our wisdom or our primal destructive urges. And a crucial factor might be human connection.
James W. Prescott's cross-cultural statistical analysis suggests exactly that. He found a strong correlation. Physical affection in infancy and adolescence links to nonviolence in adult societies, while physical punishment in childhood correlates strongly with violence, authoritarianism, rigid belief systems.
That's a profound insight into the roots of conflict and peace.
The sources state it starkly. The percent likelihood of a society becoming physically violent if it is physically affectionate toward its infants and tolerant of premarital sexual behavior is 2%. The probability of this relationship occurring by chance is 125,000 to 1.
That's not just correlation.
It strongly suggests a deep causal link, that how we raise our children, the compassion and affection we show, might be the most fundamental defense against future violence. The path to a more peaceful, sustainable civilization. It tells us our ability to thrive on this pale blue dot is just inextricably linked to how we treat each other.
Ultimately, this brings us to that profound search for extraterrestrial intelligence, SETI, and the incredible cosmic perspective it offers.
Radio astronomy is seen as the ideal method for interstellar communication, right? Relatively inexpensive, signals travel at light speed, they stand out against the background noise if you detect them.
Like the Arecibo message.
Famously, yeah. Transmitted in 1974 from that massive radio dish in Puerto Rico. 1,679 bits of information, a product of 2 primes, chosen to highlight its artificial origin.
What did it show?
If decoded, it visually represents fundamental constants, DNA structure, a human form, our solar system, the Arecibo telescope itself. A deliberate, humble greeting to anyone out there.
But this immediately raises that huge question, the Fermi paradox.
Why are they not here? Exactly. If advanced civilization should be abundant in a universe teeming with billions of stars and planets, why haven't we detected any signs?
What are the possible answers?
Many possibilities, each profound. Maybe we are the first, at least in our galaxy, in this epoch, or, more ominously, maybe civilizations inevitably self-destruct. Nuclear war, environmental collapse.
They don't make it past a certain technological stage.
Could be. Or maybe interstellar flight is just too hard, making colonization impractical. Or maybe advanced civilizations just aren't interested in exploring or colonizing. Maybe they're immortal or virtual.
Or maybe they are here, and we just don't recognize them.
That's a humbling thought, too. Like early humans trying to understand radio waves, their presence, their signals, might be totally beyond our comprehension right now.
And if we look at historical alien encounters right here on Earth, our own history gives us pause about potential contact, doesn't it?
Some sobering precedents, yeah. Like La Perouse's encounter with the Tlingit in Alaska. Peaceful, but lacking real rapport. The Tlingit saw that the ships as great birds, the sailors as black messengers. The French struggled to grasp Tlingit society.
Contrast that with Cortés and the Aztecs.
A chilling contrast, Cortés' utterly destructive conquest. Despite only a relatively small tick-gap horses, iron, crude firearms, he, aided by Aztec superstition about comets and Quetzalcoatl,
managed to vanquish a high civilization.
Completely. Leading to immense suffering, destruction of a whole culture. These histories emphasize the grave danger when one society, even slightly more advanced, meets another, especially with misinterpretation or malice involved.
If we connect this to the bigger picture, these lessons, combined with the cosmic view, lead us to Sagan's pale blue dot.
That iconic image from Voyager. Earth as a mote of dust suspended in a sunbeam, it offers an inescapable perspective.
As Sagan said, look again at that dot. That's here, that's home, that's us.
The aggregate of our joy and suffering. Every human being who ever was lived there on a mote of dust suspended in a sunbeam. It challenges our conceits, encourages humility, stresses our responsibility to deal kindly with one another. A powerful reminder to preserve and cherish the pale blue dot, the only home we've ever known.
Here's where it gets really interesting and deeply personal, I think. The ultimate message from the cosmos. It isn't about alien invasions or galactic empires.
Yeah.
It's about how we treat each other right here. On our tiny, precious world, our sources highlight this crucial truth. There will be no humans elsewhere, only here, only on this small planet. In that grand cosmic perspective, we are a rare as well as an endangered species. Every one of us is precious. If a human disagrees with you, let him live. In 100 billion galaxies, you will not find another.
That should reframe everything, shouldn't it? Every conflict, every prejudice, every act of intolerance.
Absolutely.
And this realization, it also offers a powerful redirection for our species' energy. The same ingenuity, the same tech, the same vast resources we pour into destruction like nuclear weapons
can be reinvested into life-affirming things.
Like space exploration, scientific discovery, shifting our energies from death to life, fostering that vital cosmic perspective that transcends narrow national chauvinism, petty divisions. The exploration of the cosmos, our quest to understand the universe, is really, in essence, a profound voyage of self-discovery. It shows us our true circumstance, humbles us, and ultimately challenges us to evolve beyond our dangerous evolutionary baggage and embrace our shared future as inhabitants of this unique, precious, pale blue dot. Hashtag tag outro.
Wow, we've taken quite a deep dive today, haven't we? Into the cosmic ocean, from the tiniest atoms making up everything to the largest galaxies dancing across the universe. We've explored the intricate, unfolding story of life, the amazing power of science to reveal hidden truths, and the profound implications of all this knowledge for our own unique place in this incredible universe.
It's a story that unfolds over billions of years, across unimaginable distances. Yet somehow, it brings us right back here to our shared home.
Right.
And what's truly fascinating, I think, is that consistent, unifying message echoing across all these sources, that understanding the cosmos, really embracing its vastness and our own smallness within it, gives us this crucial, maybe even necessary perspective on our responsibilities right here on Earth. It emphasizes our fragility, our deep interconnectedness with all life, and the unique, irreplaceable preciousness of this pale blue dot we call home. It really urges us to protect it.
So as you go about your day, maybe tonight look up at the sky or just look around you at the life teeming on this planet. Consider this. If we are indeed a rare and potentially endangered species existing on just one small, vibrant world in this unimaginably vast universe, what truly constitutes a universal value, something that transcends our local differences? And how might recognizing that profound truth shape how we live, how we learn, and how we choose to define our home, not just for us, but for all the generations still to come?